What if there is another fifth force in the universe, an unknown fundamental interaction of nature? At first glance it may seem unbelievable. How could we have missed an entire fundamental force with the current level of scientific advancement? But on the other hand, if we look at the question naively, in our everyday life we only really notice or experience two forces or interactions, and they are actually easy to demonstrate. Of course, that's gravity and electromagnetism. But to be fair, let me demonstrate the strong interaction now. Watch this. Well, I didn't fall apart into quarks, so I guess that counts as a demonstration? But after all, we don't think of the weak and strong nuclear interactions the same way we think of gravity and electromagnetism. If a person does not know anything about their existence and you tell them that on the scale of elementary particles there aren't just two but three or more fundamental interactions, they probably won't find that surprising. But what if the four fundamental forces I mentioned isn't everything there is? After all, we learned about the last two relatively recently, in the 20th century. So maybe this isn't the end yet, and we just haven't discovered a new fundamental force of nature yet. Meanwhile, science has been taking this question quite seriously for several decades. There have been both theories and experiments. If you dig a little, you can find articles in the media dating back to the 1980s about the possible discovery of the fifth force of nature or hints of its existence, and such articles still appear today. You may have heard the phrase new physics when scientists observe some anomalies in data or experiments, but we rarely specify what exactly is meant by new physics. So this new, previously unknown fifth fundamental interaction could be a perfect example of that new physics. So today we're going to talk about the fundamental forces of nature in general, about the search for a fifth force, what it might be, why we're looking for it, and what problems its potential discovery could solve, how scientists are searching for it, and what hints there are of its existence. And not just about that. I'm Andrei, and this is Cosmos Elementary. So we have four forces. Some might ask, what about the other forces in physics, like friction, elasticity, centripetal force, and so on? But first we need to remember the important word: four fundamental forces. These are what describe and explain everything else we call forces, and in fact, everything in the universe. Secondly, the use of the word force here can be questioned. In the simplest terms, a force can be defined as something applied to a body that makes it move, deform, or both. But you've probably come across articles or videos saying that gravity, for example, isn't actually a force. Well, it's not that simple. In any case, scientists prefer to use the word interaction instead of force, and say four fundamental interactions. I've already used both terms today, and I'll keep using them interchangeably in this video, just as established expressions, but we'll clarify this point a bit later. And in general, it's really fascinating that despite the complexity of the universe and the incredible diversity of objects, phenomena, and processes at all scales, from the macroscopic to the galactic, it's all governed by just four fundamental forces. Well, of course, unless there are some others, which is exactly what we're talking about today. Besides their function, the four fundamental interactions differ from each other in two important ways. The first thing is the distance or the scale at which they operate, and the second is their strength. And when we talk about a potential fifth force, these same two parameters are also discussed. Over what distance the force acts, and whether it is stronger or weaker than the other interactions. Actually, the concept of the four forces of nature is relatively new. As I mentioned, two of the four interactions were only discovered in the last century. The first thing, in one way or another, that was considered a force is, of course, gravity. And for that, we have to thank Isaac Newton. However, the way we view gravity has changed since then. In fact, discussions about gravity not being a force at all arise partially from this revised perspective. Newton did a pretty good job describing gravity. creating equations that are still suitable for many applications, and which were even used to launch spacecraft into space. But what he didn't do, and what puzzled him, was the fact that while he could calculate how two bodies of certain masses would attract each other, he couldn't explain how this attraction actually works. Through what exactly is this pull transmitted? As many of you probably know, Einstein later provided this description. He also unified the previously separate concepts of space and time, describing them not as mere emptiness, but as a dynamic entity that bends and curves in the presence of mass and energy. And what we call gravity is simply objects following these curved trajectories. But in this case, it almost doesn't seem like a force in the usual sense. Yet there are some complications. Gravity in the classical sense governs how bodies with mass interact with each other. It governs the motion of celestial bodies, planets, stars, and galaxies. It keeps us and our atmosphere from flying off into space and does many other useful things. We all know that. The next interaction, in chronological order, is the electromagnetic force. It depends not on mass, but on charge, and acts between charged particles. We know the whole opposite charges attract, while like charges repel thing. Charged particles are associated with an electric field, and when they move, a magnetic field also arises. Through this force, electric devices, magnets, and the magnetic fields of planets and stars work, electrostatic effects, and so on. But what's especially important for us personally is that without this interaction, we couldn't exist. Just like practically everything around us. Everything made of atoms. Here's a simple schematic of a hydrogen atom, where the nucleus is a positively charged proton and the electron carries a negative charge. It's what keeps them held together. So if it weren't for electromagnetism, atoms would fall apart, or rather they wouldn't have formed in the first place. And the universe would be a pretty boring place. Thanks to it, chemical reactions occur, forces like friction arise, and so on. So it's a very useful thing. Gravity and electromagnetism have something in common. Both interactions act over large distances. In fact, over infinity. Essentially, any object can exert a gravitational effect on any other object in the universe, provided that this influence has time to reach the body, given the ultimate speed limit, the speed of light at which it apparently propagates. Both interactions obey the inverse square law, meaning their intensity is inversely proportional to the square of the distance. If objects are twice as far apart, the force is 4 times weaker. 10 times farther, 100 times weaker, and so on. They weaken relatively quickly, but never completely disappear. So essentially, you're influenced not only by the pull of the Earth, Moon, the Sun, but also by all other planets in the solar system, and even by something like Proxima Centauri. It's just that the effect is already immeasurably small. You may know that gravity is much weaker than electromagnetism, many orders of magnitude weaker. This even leads some people to argue that since electromagnetism is stronger than gravity, it must be the main force in the universe, the one that determines the formation of cosmic objects and structures. I've already made a separate video about the electric universe hypothesis. But in fact, in the atoms that make up us and the planets, particles with positive and negative charges balance each other out, giving us neutral atoms. So even magnets much stronger than the Earth's magnetic field don't pull us in the way Earth's gravity does. In short, gravity and electromagnetism are both crucial. Without them, there would be no planets, no stars, no galaxies, and not even the kind of matter we're familiar with. But we found that electrons and atomic nuclei are held together by electromagnetism. This all makes sense. And again, we can see a similar effect ourselves when magnets attract each other with opposite poles. If we look deeper inside the atom, things become much less intuitive. The nucleus isn't made of oppositely charged particles, but of a bunch of positively charged protons and neutral neutrons. The number in the bunch depends on the element. In theory, all those protons in the nucleus should repel each other. Since atomic nuclei don't fly apart due to the repulsive electromagnetic force, there must be some other force, and it must be even stronger than electromagnetism. And that force is the strong nuclear interaction. It's about 100 times stronger than electromagnetism and is the most powerful of the known fundamental forces. Its name isn't very sophisticated and it operates on two different scales. The first is what I've already mentioned, holding nucleons, the building blocks of the atomic nucleus, together. That includes proton with a proton, neutron with neutron, and proton with neutron. But these nucleons aren't the smallest particles. They themselves are made of quarks. The strong interaction also holds them together. And finally, we have the last one, the weak interaction. The name here is a bit misleading. More precisely, it is weak, but not the weakest. It is still many orders of magnitude stronger than gravity. A weak nuclear interaction is probably the most unintuitive. The function and effects of the previous three forces are fairly easy to grasp. When the weak interaction is briefly described, people usually say that it's responsible for certain types of radioactive decay, particularly beta decay. Well, and that's a bit less obvious than let something go, it goes down. The weak interaction is responsible for the interactions of subatomic particles. For example, protons and neutrons are made of quarks. But quarks come in different types. Here we have U and D quarks, also called up and down quarks. I should remind you that these names have nothing to do with spatial orientation. They're just convenient labels for the letters U, up, and D, down. Hence, up and down. A proton consists of two up quarks and one down quark. A neutron, on the other hand, is made of two down quarks and one up quark. So, for example, when the weak interaction affects a down quark and a neutron, it can turn into an up quark. The neutron then becomes a proton. The reverse process can also occur. The particle's charge changes and a neutrino and either an electron or a positron are released in the process. If that neutron was a part of an atomic nucleus, the atom can turn into a different element. As we know, during radioactive decay, some isotopes transform into others, releasing additional particles in the process. The weak interaction plays an important role in both the decay and nuclear fusion reactions in the cores of stars, so it affects us as well. Unlike gravity and electromagnetism, the strong and weak nuclear interactions don't act over infinite distances. On the contrary, they operate at extremely small scales. The strong interaction drops off beyond about 10 to the power of minus 15 meters, roughly the diameter of a proton. The weak interaction, however, operates on even smaller scales, no more than 10 to the power of minus 18 meters. That's 1,000 times shorter than the range of the strong force, and about 1,000,000 times weaker. And if we compare the weakest force, gravity, with the strongest one, the difference is staggering. The strong interaction is about 100 trillion times stronger than gravity. But again, because of its extremely short range, we don't feel it in the way we do gravity. Still, it's the reason we don't fall apart into subatomic particles. I have just briefly described the functions of four interactions. We can see that the functions of some forces are more obvious than others. And it's not too hard to imagine that there might be another force, one with less obvious role, like the weak interaction. We can also draw a preliminary conclusion. If we're thinking about adding something else to this category, alongside the four known interactions, then it too should have certain parameters, a specific range and strength. Is it stronger than gravity? Weaker than the weak interaction? Does it operate on the tiny scales of particles or over large distances? Depending on these parameters, the fifth force might be harder or easier to detect. For instance, if it operates on even smaller scales, or if its effect is extremely weak, we simply might not be able to detect it with today's available equipment. But that's not all when it comes to the forces we know. I've said what they do, but not how they do it. Here we need to briefly mention the carrier particles, And this is also where some issues of modern theories start to appear. So when we talk about interactions, we mean that particles somehow affect each other. Let's say we have two protons held together by this strong interaction. But how exactly does it keep them together? I mean, physically, what is it? Because as it stands, it sounds like some kind of magic, and scientists weren't satisfied with that either. And we now think that fundamental interactions work like this. Particles exchange special force-carrying particles called gauge bosons. With one caveat though. The particle that carries the electromagnetic interaction is the photon. For the weak interaction, it's essentially three particles. The W bosons, W stands for weak. There are two because one has a negative charge and the other a positive charge. Here the charges are indicated with a plus and minus. And the Z boson has zero charge, which is why it is called Z, for zero. The particle that carries the strong interaction is the gluon. All of these have been experimentally observed and are part of the standard model of elementary particles. But you may have noticed that something is missing. Yes, the force-carrying particle for gravity, the graviton, because its existence hasn't yet been experimentally confirmed. Some scientists speculate that it might exist, but for now this particle is purely hypothetical. This is one of the obstacles to developing a quantum theory of gravity. We can also recall that from the perspective of quantum field theory, all particles are not just, well, let's say little balls. They are disturbances in quantum fields. Each particle corresponds to its own field, and all these fields permeate every point in space. A particle is a disturbance in a field with higher energy. Accordingly, each fundamental force has its own field. For example, the gluon field. And the force acts when a particle, say a proton, interacts with that field. So if each interaction corresponds to its own particle or field, then the one we might call a new fifth fundamental interaction would also need its own force-carrying particle. It would have its own parameters, mass, charge, and spin. Once again, since we're talking about fundamental interactions, we can't ignore the idea that these very different at first glance forces might actually have a common origin, be a manifestation of a single, let's say, master force of the universe. And at the very high energy levels, they could unify. That in the earliest moments of the universe, when it was extremely dense and hot, there was a single unified force, which later, through phase transitions, gradually split into the four forces we know and love today. And this idea has been partially proven in laboratories, or more precisely, scientists have so far managed to unify electromagnetism and the weak interaction into the electro-weak interaction. Today, physicists are working on further unifying the electro-weak interaction with the strong interaction within the framework of grand unified theories. But so far, this hasn't been achieved. And the famous theory of everything aims to unify all four interactions. Though to do that, a quantum theory of gravity still needs to be developed. But here, in the context of unification, we're talking about the four forces that we still can't fully unify. So what if a fifth one actually exists? That would make the situation even more complicated. So what do we have at this point? If a fifth force of nature exists, it should have its own force-carrying particle, which in principle could be detected. It would need to operate over a specific range and have a certain strength or magnitude. The known fundamental interactions are described within the framework of the standard model of elementary particles. Gravity has a bit of its own thing. But as I've said many times, the modern standard model is very successful. It describes a vast number of processes and phenomena in the universe and makes accurate predictions. But what could indicate the presence of a fifth force? Well, for example, some anomalies and deviations from the standard model. For example, scientists study the behavior of particles in accelerators, and everything that happens to them in experiments fits perfectly within the standard model. But if we suddenly observe some anomalies, say a particle behaves in a way that's not predicted by the standard model, then maybe something else is influencing it. Could these deviations be caused by some unknown fifth force? That's something we can actually try to test experimentally. And we should also remember that, successful as it is, the Standard Model is far from a complete or final description of reality. It has its problems, and a fifth fundamental interaction could potentially help explain some of them. Scientists consider many possibilities for what a fifth interaction might be. Proposed variants of the fifth force can act over very short distances like the weak and strong forces, others over much larger scales. The strength of their effects can also vary. The reasons scientists start discussing a fifth force and what they try to explain with it are similarly diverse. It might be an attempt to fill gaps in current theories or to account for anomalous experimental results. Scientists have actually been speculating about the fifth force for several decades, and the very term may have originated in the mid-1980s. After the publication of a paper by Ephraim Fischbach and his colleagues in which they reanalyzed the data from the Ötvös experiment. This experiment, conducted with ever-increasing precision, confirmed the equivalence of inertial and gravitational mass. However, Fischbach's team reanalyzed the data and suggested that gravity might vary with distance. Specifically, it could deviate from the expected inverse square law we discussed. They concluded that there might be some unknown force at work here, similar to gravity but weaker. In the original paper, the term fifth force wasn't used, but as Fischbach himself recalled in an article discussing the whole story and its later developments, journalists dubbed it the fifth force, in a New York Times piece inspired by the research. However, this path didn't lead to the discovery of an actual fifth force, and other scientists were unable to reliably reproduce Fischbach's team's results. But why do scientists keep looking for it? As I've said, the Standard Model is good, but not perfect. It's, for instance, plagued by the issues like dark matter and dark energy. Take dark matter, for example. I think many of you already know that today it is believed that the universe contains some hidden form of mass, about 5 times more than the ordinary matter we can see, the stuff that makes up us, the planets, the stars, and everything else. And this matter is needed to explain, for example, the speeds and motions of stars within galaxies, as well as the behavior of galaxies and clusters. Over the past few decades, a lot of evidence has accumulated supporting the existence of this hidden mass. There are some alternative ideas, though, among which is the idea that we're describing gravity incorrectly, though this idea is less popular and has more drawbacks. The problem is that, even if this hidden mass exists, we don't actually know what it is. There have been ideas that it's just objects made of ordinary matter that we can't see, which wouldn't require new physics. Lots of dim objects like brown dwarfs or clusters of black holes have been proposed, but these ideas haven't been strongly supported either. Then dark matter might not be made of macroscopic objects, but some kind of particles. Well, there's a problem. Of all the known particles in the Standard Model, none have properties capable of explaining the behavior of this dark matter. And this is where a whole host of hypothetical particles appear as candidates for dark matter, some of which could potentially be linked to the unknown forces of nature. Take, for example, probably the most popular class of candidate particles today, WIMPs, which stands for Weakly Interacting Massive Particles. Dark matter is often described as interacting with ordinary matter through gravity, but not through the other fundamental interactions. That is, it's affected by gravity but not the other forces. But if among the 4 known interactions only one acts on it, could it then be influenced by other unknown forces? There are even ideas about how these mysterious forces might affect dark matter, and that hypothetical particles could exist through which this influence is exerted. They have a very cool name: dark photons. These are like a dark analog of the regular photon interacting with the charge in a similar way. Unlike ordinary photons, in some versions, dark photons have mass. What's even more interesting is that if they exist, dark photons could interact with ordinary matter and even decay into particles we can already detect. There have even been experimental attempts to observe this, which I'll talk about a bit later. This isn't the only hypothesis linking the fifth force to dark matter, nor the only possible way to detect it. Their ideas about how a long-range fifth force associated with dark matter could affect the orbits of celestial objects, and this could potentially be detected through astronomical observations. There are other possibilities as well. Another problem, of course, is dark energy. It is the observationally confirmed fact that the universe isn't just expanding, it is doing so at an accelerating rate. According to modern models, this requires a tremendous amount of energy, which accounts for the majority of the universe's mass energy content. Again, we don't know what it actually is. It could be a property of space-time itself, but the accelerated expansion might also be caused by some as yet undiscovered fundamental force of the universe, the fifth force. There are some scientific papers about this as well. In recent years, discussions about the fifth force have become more frequent. Not just due to purely theoretical considerations, but because of anomalous results in some experiments. In 2015, a group of Hungarian scientists conducted an experiment in which they bombarded lithium targets with a beam of protons. The scientists were trying to study the very dark photons I mentioned earlier. As a result, excited beryllium-8 nuclei were formed, which then immediately decayed into regular beryllium-8 and pairs of electrons and positrons. Usually after the decay, this electron-positron pair flies off in the same direction, but authors of the study claimed that in a small fraction of decay events, they flew off at a different angle. Behavior not predicted by the standard model. So that's an anomaly. Known physics can't explain it. The question then is, what is causing it? They suggested that this effect might be caused by a previously unknown particle, a boson roughly 33 times more massive than the electron, with a mass of 17 million electron volts, which led it to being called the X17 particle. And another group of scientists suggested that this particle might be related to the fifth force, perhaps even be its carrier particle. However, there were questions about the Hungarian group results, because previously they had claimed nearly 10 other anomalies and candidate new bosons, which seemed highly unlikely, and their previous findings were largely refuted. There were also questions about how they handled the data. Overall, this line of research hasn't yet led to new physics. Another example of experimental hints at the fifth force was found in data from experiments at the Large Hadron Collider. Data from one of the detectors showed an anomaly. The scientists were studying the decay of beauty quarks. Of course, they aren't literally beauty, although… excuse me. Here, as with up and down, beauty or bottom quarks comes from the letter B in the name. So they're supposed to decay into electrons and muons in equal proportions. But for some reason they decayed into muons 15% less often, something not predicted by the standard model, and again possibly caused by an unknown force of nature. There isn't enough data yet to draw any conclusions about a discovery. For now, this could be just an error in measurements or data interpretation. Perhaps new data will settle the matter. And another high-profile story related to the fifth force concerns the muon G2 experiment conducted at Fermilab. The idea is that muons, particles similar to electrons but about 200 times heavier, when placed in a magnetic field, should wobble in a specific way. And the character and frequency of this wobble is predicted by the standard model. And experiments at Fermilab showed a deviation from the expected behavior. Moreover, even over 20 years ago, experiments at Brookhaven National Laboratory showed a similar effect. It is possible that this anomaly is caused by an unknown particle or an unknown fifth force of nature. In more recent experiments, it was concluded that the statistical significance of this observation was high, 99.98%, indicating that it's unlikely to be a random deviation and likely represents a real effect. This sounds like a lot, but in particle physics, where the standards are very high, a discovery claim requires a confidence level of 99.99994%. And later, new results from this experiment were published, and the effect was still observed, with its statistical significance seemingly reaching the level required for a discovery. But it also turned out that there are some theoretical uncertainties. So once again, it's too early to talk about the discovery of a fifth force. You would definitely have heard about it, because it would be a breakthrough in physics. Now it would be good for other research groups to study this effect in independent experiments and gather more data. Could a fifth force of nature exist? Quite possibly. The standard model is almost certainly incomplete. What we've discovered so far is all there is. This applies even to the fundamental interactions. Research continues, new theories are being developed, and investigations are underway both through astronomical observations and laboratory experiments. So it's not impossible that one day we'll hear about the discovery of a fifth force of the universe. And maybe later, even a sixth? Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more videos in future. Bye.